here we are. We're back. We're doing take two because last time partway through the live stream earlier today, I clicked a button that stopped sharing the screen. So that wasn't good. Uh, so I guess I'm going to start again from the beginning because I promised I would do live streams. And I'm not going to wait till tomorrow to do this again. Okay, so today the first thing I want to talk about is why. So this whole first week, probably. I don't know if you're at a different university and you're watching this, but we talked about row echelon form and reduced row echelon form, and row operations of matrices. But the question, why are we doing all this, right? Is it just because your professors were like, ha ha ha, let's make them do math. Let's put numbers in a grid and just give them some rules and see what happens. Like, that'd be funny. No, actually, even though it might feel like that sometimes, it turns out there's a point to all of this linear algebra stuff and these row operations and row echelon form and everything like that. We're doing these things for a reason. What is that reason? Well, the general process of what we do is, say you start with a system of equations like 3x plus 2y equals 1 and x minus y equals 3. We start with this system of equations, and what we do is we turn this into an augmented matrix. So in this case, we would write 3, 2, 1, 1, minus 1, 3. And then we do some stuff, right? So let me make a more abstract map. So we start with a system of equations. We turn it into an augmented matrix. Then to that augmented matrix, we apply a bunch of row operations, and we get a reduced row echelon form matrix. And then we turn this back into a new system of equations, right? And we solve this system of equations. Well, why? Right? We started with this system of equations over here. Why are we solving this other system of equations? And why are we doing row operations? And why do we care about reduced row echelon form? The main point is that any solution to the original system of equations is going to be a solution to the other system, the system of equations we get out of the reduced row echelon matrix. And vice versa. So we know that if we can solve the system of equations from the reduced row echelon matrix, any of those solutions are going to be a solution of the original system of equations. So that is actually why we care about row operations. The reason why it's those three operations of multiplying a row by a scalar, adding scalar multiples of rows, and swapping rows is because those are exactly the things, the operations we're allowed to do to change a matrix that won't affect the solution set of the corresponding system of equations. So it's not just random and chaos. There is a reason to it. Now, hopefully, maybe I'll put up a separate video, or I'll talk about this in the live stream next time. Well, I might have to wait a little bit, because the question is why, right? Maybe you're like me, you want to know, well, okay, I don't get it though. Why are those row operations the things that don't affect the set of solutions? That might have to wait for a little bit until later in this course when we start talking about linear transformations. And then once you have some of that language, it might be easier at that point to come back to this and understand why those row operations, why those are the things allowed and not like anything else. Yeah, so we'll come back to that. But then, so that still leaves the question of why reduced row echelon form? Well, in general, this is easier to solve as a system of equations, right? So like, we have this system of equations up here, like fairly complicated, but you can imagine, okay, I haven't solved this yet. I don't, I haven't solved it yet, but it's gonna, like, if it has a unique solution, for example, it's gonna look something like this. So, okay, just to be perfectly clear, I am not saying I'm not saying this is the ref of the above. Okay, I'm not saying that. I'm just giving an example. It could look something like this. And then if we pull out the system of equations here, well, this is a lot easier, right? X equals 2 and y equals -5. We can just read it basically directly off of this matrix of the solution. Now you might say big whoop, right? Like, because in high school, you would have taken the system of equations and you would have solved this using elimination. And you would have used substitution, right? Where like you isolate for x and then you plug that into this part of the equation and you just solve. And, probably that's a lot faster and simpler to solve the system of equations. So why would I bother, right? I'm telling you that, oh, the reduced row echelon form is easier to solve. And like, okay, cool, sure. Like, but if it takes me a lot of steps to get to reduced row echelon form and like set up this matrix and everything, why would I bother if it is just easier to work with this original system? Well, the reason is for if we have two equations and two variables, for sure, this is an easier system of equations to solve. But what if we have something like 4 equations and 4 variables, or even 3, right? Even if we had 3 and 3, it's like 2x1 plus x2 minus x3 equal to 1, x1 minus x2 minus 7x3 equal to minus 15, and like 7x1 minus 2x2 plus 5x3 equal to 0, right? Like, if you tried just doing elimination and substitution here, then it would actually be a lot longer and way messier, right? Like, if you think about all the substitution of variables and stuff you'd have to do here, like could you imagine if you took the second equation, for example, and you isolated for x, so you got, it would be x2 plus 7x3 minus 15, right? And then you took this and you went and you plugged this in for x equals 1 into the other 2 equations, and then you had to multiply out these constants and all this. No, it's so messy. It's so messy. It's going to take you such a long time. And that's just for 3 variables and 3 equations. Never mind like 4, 5, 6, whatever. Which, okay, though, that's just going to take a long time by hand. No matter what you're doing. Oh, I'm just gonna, I don't think there's anyone here right now, but I'm gonna make sure the chat is working. Don't be afraid to say hi in the chat if you're here. I'm gonna try and watch it. Okay. So coming back to our system of equations, and yeah, so it's a lot longer. And so the reason is, so if we have more variables or more equations than just 2, then really this is, as originally advertised, this is the easier way to solve a system of equations. We take that system, turn it into an augmented matrix, and then using row operations for larger systems is actually going to be better than elimination and substitution. It's going to be less messy, which means less chance you're going to make mistakes. And it's probably going to take less time too, almost like definitely. And then we get into a reduced row echelon form. And that's going to be a nicer, right? That's going to be an easier system of equations to solve, even for the 3x3 case. Again, so I'm not saying that this is what this is going to look like. I can't just do this instantly in my head, but it could be something like 1, 0, 2, minus 1, 0, 1, 0, 3, 0, 0, 0, 0, for example, right? So let's just pretend, right? This is the, we'll do an example soon. Let's just pretend this is a reduced row echelon form of a matrix that we get out. Sorry, I'm going to come back and check this dashboard for my stream because I'm paranoid I'm going to make the same mistake and click on something stupid again. Yeah, so if we're looking at this reduced row echelon form, right, and now we try and solve this system of equations, right? This says what? This says x1 plus 2 x3 equal to minus 1. This second row just tells us, boom, x2 is equal to 3. We don't even need to do anything. We can just solve this instantly. And then this bottom row, whenever we have a row of all zeros, that means we have a free variable. So, we can just let x3 be just any real number we want, actually. So this system, for example, would have infinitely many solutions. And maybe after the stream, we're going to go over some row echelon form examples in a minute. So maybe after the stream, or I mean towards the end, I'll talk about more precisely the difference about how we know if there's infinitely many 0 or 1 solutions. So yeah, I mean, this is a way easier problem to solve. So that is why we do reduced row echelon form, because it's basically, it sets up the matrix to give you the easiest system of equations to solve possible that is related to your original set of equations, right? So you have your original system, and then you could go to, I mean, just row echelon form is sort of an in-between place, right? There's 3 things that define row echelon form, so it's definitely easier. And then reduced row echelon form is easiest. And it's definitely better to put things in reduced row echelon form. Okay, so enough about me, talking philosophically about all this stuff. Let's do some worked examples, right? Let's go through some of this. I made up this example up above, 3x plus 2y equal to 1x minus y equal to 3. I think that's what I did. So let's try it. Let's do it. So we first write down the augmented matrix. So that's going to be 3, 2, 1, 1, minus 1, and 3. Okay, and so, well, what does it mean? So first off, what we want to do before we get to reduced row echelon form, we want to get to row echelon form. So what does it mean to be in row echelon form? Well, let's go check the definition. Should have the textbook open here. So on the textbook for the course, I think I might have to add the link to the description below, but it is in the description of the very first video. I gave the textbook that I'm using for the course that I'm TAing, although, it shouldn't be very different if you're watching these live streams coming from a different university. So the definition here is definition 1.2 of a row echelon matrix. So condition 1, we need to make sure a matrix is row echelon form if it satisfies all 3 of these conditions at the same time. So let's check if that's true. So condition 1 is that all non-zero rows are above any rows of zeros. So let's go look at our matrix. Well, there's no rows of zeros, right? So automatically all our non-zero rows, which is both of our rows, are above any rows of zeros. Great. Okay, nothing to worry about there. Let's check condition 2. So each leading entry of a row is in a column to the right of the leading entries of any row above it. Okay, I realize that one's worded a little trickier, right? This one's a little harder to process. So each leading entry of a row is in the column to the right of the leading entries of any row above it. So let's check, right? What's our first leading entry here? So we look at our first row. Our leading entry is the first entry, which is not 0. So we look at our first entry, which is not 0, and that is just the first entry, which is 3. And let's check. Well, it's got to be to the right of any leading entries in any rows above it, but there's no rows above it. So yeah, there's really nothing to check here. Okay, great. So let's check the leading entry of our next row. Well, it's got to be this one, right? This is the first entry that's not equal to 0. And well, now we can see a problem, right? This is certainly not to the right of the leading entry in the row above it. It's directly on top of. So that's an issue. So what that means is one of these leading entries has got to go. Which one? Well, what could we do, right? We have our row operations, right? Those row operations, those are things we're allowed to do in order to try and get our matrix into reduced row echelon form. So I could either knock out the 3, right? So I could take row 1, and what could I do to row 1 to get rid of that 3? Well, I could take this bottom row. I could take row 1, and I'm allowed to subtract scalar multiples. So if I did 3 times the first row, then I'd get 1 times 3 down here, and I could subtract that off to get rid of that 3. Right? So that's one option. The other option is I could try and get rid of this 1. Right? So instead, I could try and change row 2, and I could try and change row 2 by taking it. And well, what would I have to do here in order to get rid of this 1? Well, I could divide row 1 by 3 and then subtract it off, right? So that's the same thing as multiplying by minus 1/3. But, if we look at this, yeah, that'll get rid of this 1 down here. But then if you think about, what's going to happen, these other entries, these aren't divisible by 3. So I'm going to get all these nasty fractions in here, and that's terrible, right? Like, I'm sure probably a lot of you watching this have nightmares about fractions and doing math with fractions. Like, they kind of suck. So we should avoid doing math with fractions if we can, right? It's like sometimes you just got to use it, right? Sometimes you got to divide your cake up amongst your friends. But it's always easier if things can be divided up nicely and evenly, right? So let's not do the second option, right? Because gross. Fractions are gross. Let's not do that. Let's go with option 1. So row 1 is going to change. I'm going to subtract 3 times row 1 from it. So 1 times 3 is 3. So 3 minus 3 is 0. Minus 1 times 3. So here's where we got to be careful, is when there's double minus signs popping up here. So I have 2 in the first row, and it's going to be minus 3 times whatever that entry is in the second row. So it's minus 3 times minus 1. And so here I actually get a double negative. So it's going to be 2 plus, because negative times negative is positive, 3. So I'm actually going to get 5 in this first row. And then, so I have 1 minus, so 3 times 3 is 9. So I get 1 minus 9 is going to be minus 8. And now I look at the, well, the bottom row is the same, right? We're not doing any row operations to it this time. Okay, great. So is this in reduced row echelon form yet? Well, condition 1, again, is about rows of zeros, and we don't have any of those, so there's really nothing to worry about. Condition 2, this is about the leading entries, and so we need the leading entries to be the right, to the right. So our leading entry of the first row, now it's this 5 here, because that's the first non-zero entry. And the leading entry of our second row is now a 1. Oh, wait a second. The matrix operations we just did was to try and solve this problem, and we haven't really solved it. Oh, I mean, we stopped it being the case that the two leading entries were on top of each other. So, I mean, I guess that's good. But remember, if we go back to the screen here, it says each leading entry is in a column to the right of a leading entry above it. So I'm just checking, make sure everything is still here. Yep. So now if we look at this leading entry down here, it's to the left of the leading entry above it. And that's not what we wanted. But we have more row operations at our disposal, right? What could we do? What else could we do here? I'm pausing for a dramatic effect. Hopefully, so I don't have any. Originally, I was thinking about putting on some like copyright-free lo-fi hip-hop study beats, but maybe some of you don't. Some people can't listen to music while they're studying. So what I'm going to suggest actually is, if you want it, put on whatever music you can study to while you're watching this video, because some people can't. So I'm not gonna put it in this video beforehand. You'll just have to do it manually. Okay, so looking at this, I've given you a minute to think about it. So hopefully you had this idea, and what it is I can just swap row 1 and row 2. And look what happens when I swap them. So row 2 is going to come to the top. So I get 1, -1, and 3. And now 0, 5, and -8 at the bottom. Okay, so again, no rows of zeros. That part is fine. We look at our leading entries, and okay, I've got a 1 here. I've got a 5 here. Great. And so now there's no rows above the first leading entry, so there's nothing to worry about there. And then for the next leading entry, it's now to the right of the leading entry above it. So that condition is satisfied. Okay, so boom, we got 2 out of 3. And according to Meatloaf, 2 out of 3 ain't bad, but we still have, if we want to do row echelon form, we got to do the full thing. So each leading entry of a row is equal to 1. That's a condition we're missing right now. So if we go back and we check that out, well, it's true of our first row, right? Our leading entry is equal to 1. But our second row, the leading entry is equal to 5. Now, here's where we have to be careful, because there's, again, there's 2 ways we can do this. And unfortunately, both of them are gross this time. So the thing that we should do in this case is just take row 2 and divide it by 5. So just become, multiply by 1/5, right? And that's the 5 divided by 5 is gonna give us a 1, and that's fine. The other thing you might be thinking, though, because it's like, a fraction, could we do something else to avoid it? You might be thinking, well, what if we took row 2 and instead we did row 2 plus 4 times row 1? Doesn't that look nicer? And yes, it looks nicer, but let's see what's going to happen here. If we went plus 4, then, okay, so our row 1 looks the same. But now here's the issue, is that 4 times 1 is 4, and 0 plus 4 is 4, right? -1 times 4 is -4, so 5 plus -4, well, 5 minus 4 is 1. And then here we'd have 3 times 4 is 12, -8 is 4. So we accomplished what we wanted to do, right? We wanted to take that 5 and make it into a 1. But now something else happened, is we ended up going backwards, right? We ended up getting these 2 entries on top of each other. So you also have to be careful, right? Our whole goal, we're trying to do this in order to get to reduced row echelon form, right? And we want to make sure that every step of these, in order to make sure we're not just going in circles, we want to make sure that every step of our matrix operations is bringing us closer to that goal of reduced row echelon form. And here we're kind of moving backwards, because now, right, we did all this work to make sure these two entries weren't on top of each other, and now that's back. So this is bad, right? We don't want this, but thankfully there is something we can do that's going to avoid this issue, right? So we're going to do this other row operation. And unfortunately, sometimes you just got to work with fractions. So like I said, avoid them if you can, but sometimes you can't. So 0, of course, divided by 5 is still 0. 5 divided by 5 is 1. And now we get minus 8 over 5. Okay. Could be worse. So let's go back. Let's check our definition of what it means for a matrix to be in row echelon form. All non-zero rows. Okay, well, I think by this point you probably know what the definitions are, right? All the non-zero rows have to be above all the rows that are all equal to 0. And yeah, we don't have any rows that are all equal to 0. So done. Good. All the leading entries have to be to the right of the ones above them. So that hasn't changed, right? We've got our leading entries, and as we go down, they shift to the right. Perfect. And then finally, the last one simply says that all the leading entries have to be equal to 1. And yeah, now we have that. So this matrix is in row echelon form, which we could probably go ahead and just try and solve for right away, solve for it right now. But, and this is fine. Again, for a system of 2 equations and 2 variables, this is probably fine. It's the perfectly reasonable thing to do. But if we had a system of more variables, so like here, it doesn't look like there's a big difference between row echelon form and reduced row echelon form. But again, if you get a system with more variables, the difference between row echelon form and reduced row echelon form becomes a lot bigger. So we do want to try and do something to reduce this to row echelon form. Sorry, reduced row echelon form. So what we're going to do then, well, what's the difference? First off, what is the difference? Well, let's return to our definition. Okay, we know what row echelon form is. So we go down to our next definition of reduced row echelon form. And notice it has more conditions, right? Oh, there's 4 things, but you don't actually have to memorize a whole extra 4 things, because if we zoom out, we look, the first 3 conditions of row echelon form, these are the exact same as the first 3 conditions of reduced row echelon form, right? So the only thing that's different is we basically copy pasted the first 3 conditions, and then we tacked on this one extra step, and that says all entries in a column above and below a leading entry are equal to 0. So let's see if we have that. So I go back to my matrix here, and let's look at our first leading entry. Well, if we look at the leading entries above it, well, there are none, so nothing to worry about. And we look at the leading entries below it, and yeah, all of them are equal to 0. Great. So let's look at our other leading one. Now, if we look at the leading entries above it, they're not all equal to 0. So we need some way to knock that out. And now, here's the reason why. So before, right, there was this the strategy that we decided was going to take us backwards, that involved adding multiples of rows together. Now, because we've knocked out this 0, we don't have to worry about what's going to happen to the left of this leading one that is on the bottom row. So we can go ahead and do whatever we want, basically, to try and knock out this one above. So we could simply just add 1 to it, right? So what I'm going to do here is I'm going to take row 1, and I'm going to turn it into, since I have a 1 in this row right here, I'm just going to turn it into row 1 plus row 2. So now, well, I get 1 plus 0 is equal to 1. Minus 1 plus 1 is equal to 0. Okay, Yeah, this next one sucks. I know. So we're going to get 3 plus -8 over 5. In other words, it's 3 minus 8 over 5. Well, we need the fractions to have a common base, right? So we use our special trick, sorry, of multiplying by 1, but writing 1 in a silly way, writing it as 5 divided by 5. So multiplying the 3 into the numerator here, 3 times 5 is 15 over 15 minus 8 divided by 5. And now the denominators are the same, so we can add these fractions together, and we're left with positive 7 over 5. So we have 7 over 5. And then down below, right, we're not changing row 1, so that is all fine. And now, okay, let's see if we're in reduced row echelon form. So no rows of zeros, nothing to worry about. Leading ones go down, go to the right as we move down. Yes. If we check the all the entries above and below our leading ones, they're all equal to 0. Perfect. And our leading entries are in fact equal to 1. So yeah, so now this is reduced row echelon form. We've satisfied all 4 conditions of the definition at the exact same time. And so now, if we try and solve this system of equations, it's much easier. We can basically read it right off, right? So remember that x, the entries in the first column are the coefficients of x. The entries in the second column are coefficients of y. And then we have our constants. So this is 1 times x plus 0 times y is equal to 7 over 5. And then 0 times x plus 1 times y is equal to minus 8 over 5. But writing this less stupidly, right? 1 times x is x. 0 times x is 0. So this is just x equal to 7 over 5. And y is equal to minus 8 over 5. And now we have our solution. Right, so there's only, in this case, there's only one solution, right? This, we just figured out we're forced to have x equal to this number and y equal to this number and no others. And then by all the philosophical ranting I did above, which will explain eventually why it's true, any equations, right, any solution to this new system of equations should give us a solution of our original system of equations, right? That was the whole point. That was the whole point of doing reduced row echelon form, right? So here's our original system of equations, and I'm not going to do it because I'm a lazy mathematician, but you should check, right? You should plug these solutions in to make sure I haven't been lying to you, right? You should go 3 times 7 divided by 5 plus 2 times minus 8 divided by 5. And you should check that this works out to 1. And then you should also check this for the second part. I mean, you may not necessarily have to do the checking on a test, but I mean, that is the whole point of doing all this machinery. As I said earlier, the whole point of this is to start with a system of equations. You turn it into an augmented matrix. You use row operations specifically because those are the things that don't affect your solution set. To get it into a reduced row echelon matrix, the reason why we do reduced row echelon matrix is because we know that the system corresponding to it is like the easiest possible version of that system of equations. And then we're guaranteed that the solutions will be the same between these two systems of equations. So you should go and check this. Okay, let me check the chat. Yeah, I don't have anyone here right now, which understandable. I messed up. I made some mistakes. I ruined my last stream, and now I'm streaming an hour later than I said I was going to be. But let's keep going. Let's talk about some things here. So let's look at these examples from the textbook. So these are matrices that are not in row echelon form. And I guess I'll just go over the details of these, and then maybe we'll call it a day for the stream, whatever time it is, even if it's not an hour. I know I promised an hour, but no one's here right now. So the following augmented matrices are not in row echelon form. So let's think about why, right? So we look at this first matrix, and okay, see some rows of zeros. So we should think, right, there's something about rows of zeros in our definition. So I scroll up, check my definition. Oh yeah, what was that thing? Let me check the definition again. All non-zero rows are above any rows of zeros. So we go down, well, here's a non-zero row, right? 1, 2, 3, 3, but that is below a row of zeros, right? So that's not allowed. So this matrix is not in row echelon form. Okay, let's look at this next one. So there's no rows of zeros, so there's nothing to worry about there. But again, we think about condition 2. It says our leading entry should be going down and to the right. But look at this. The first entry in each of these columns is a leading entry. They're stacked on top of each other, so that is the issue. And in this case, not also, so part 3 is also an issue because all the leading entries should be 1. And so we have a leading entry of 2, and we have a leading entry of 4. Notice, though, in our first matrix, all the leading entries we had, which is just this one and this other one, those at least were equal to 1, right? So there was really just one of the things was missing from this matrix. It looks like this matrix, there's 2 things that are missing from it. So it'd be a bit more work to get that in reduced row echelon form. And then finally, okay, so we look at this last matrix. Well, again, there's no total rows of zeros, so there's nothing to worry about there. Again, we look at our leading entries. We have a 1 stacked on top of a 7, so that's not allowed by condition 2. And it also doesn't even satisfy condition 3, right? Because here's a leading entry that's 7, that's not equal to 1. Here's a leading entry that's a 2, that's not equal to 1. So let's look at some matrices that are in row echelon form. So the first one, right, let's check. Well, all our rows, we do have rows of zeros this time, and all of them are at the bottom. So great, that works. Let's check then, what about our leading entries? So we have a leading entry in the first row, okay. Then we go down to the next row. It looks like that leading entry, it's to the right of the one above it. Good, that's what condition 2 says. Let's check the next leading entry. And good, that's also to the right of the one above it. Okay, condition 2 is satisfied. And all our leading entries, right, we've got 1, 2, 3 leading entries. They're all equal to 1. So boom, this is row echelon form. Is it reduced row echelon form? No. So condition 4 says all the entries above and below our leading ones have to be equal to 0. Again, our first one is satisfied, right? Because there's nothing above it, and everything below it is equal to zeros. But if we check out this other leading 1 here, sure, there's zeros all below it, but there's a 6 above it. And so not being equal to 0, so it's not reduced row echelon form. We'll look at this next matrix then. So checking out this next matrix, again, we do have a row of zeros. It is at the bottom. Great. I should double check just to point out. Someone in the class as TAing had pointed out, they thought that there had to be a row of zeros. There doesn't have to be a row of zeros to make something row echelon form. The rule is only that if you have a row of zeros, it's got to go down on the bottom. But it doesn't say that you have to have a row of zeros. Okay, getting back to this. So yeah, our rows of zeros are on the bottom. again, if we look at our leading ones, I wish I could just draw diagonally on this. I probably have an editing thing. I'll worry about it next time. So if we look at our leading ones, yeah, they go down into the right. Great, that's satisfied. And yeah, all the leading entries are equal to 1. Perfect. Let's see, everything's working right. Okay. So then, okay, we look at this third matrix here. And yeah, again, all the conditions are satisfied. Row of zeros is at the bottom. Leading entries go down into the right, and they're all equal to 1. Oh, but we should point out again, neither of these other examples are reduced row echelon form, again, because we can see some of our leading entries. This one has a 3 above it, right? This one has a 5 above it. In this one, the first 2 columns are good to go, right? They've only got zeros above and below, but then it's this third column that ruins it, because we got this 4 and we got this 6. Okay, finally, we're going to look at our matrices in reduced row echelon form examples. So these are matrices that should satisfy all 4 of them. And yeah, let's see. So yeah, we got a row of zeros. It's at the bottom. Well, I'm going to do this a little differently. I'll check the condition for each of the matrices at a time, right? So first one, row of zeros, it's at the bottom. Second one, it's got a row of zeros, it's at the bottom. Third one, no row of zeros. So there's nothing to worry about in that case. Okay, next entry. So next thing, leading ones are down and to the right. Well, here's our first leading one. Here's the next leading one. Yeah, we ended up moving to the right. Next leading one, yeah, move to the right. Same thing happens with the second matrix, and same thing happens with the third. Leading entries going down and to the right. We also check all of our leading entries in each of these matrices are equal to 1. So now we've confirmed at least that all 3 of these matrices are in row echelon form. And now the kicker here to make sure they're in reduced row echelon form. So we look at this first leading entry. Yep, all zeros above and below. The next leading entry, yep, all zeros above and below. Now you might think, oh, this is a problem. I've got this 2 on top of this 5. That's not an issue, because the fourth condition is only about the leading entries. You could have other entries, and those can be stacked on top of each other. It just says no leading entries can have any zeros above or below them. And then, yeah, we look at this last leading entry. Again, all zeros above and below. Great. So first matrix, reduced row echelon form. Second matrix, I mean, this is a pretty easy one to look at. I mean, we can see there's no other non-zero entries other than the leading ones. So those ones, pretty quick to verify. So I think I'm going to end it there. I realize I'm cutting it a little bit short, but that's just too bad. I got stuff to do too. I have my own homework to work on. So I hope that you find this helpful. You found this lesson helpful. If you did, please let me know. Please leave a comment. If you have questions, leave a comment. Next weekend, I'll have to update you guys. I might be going on a bit of a camping trip. So I might end up having to push the live stream either later Sunday or later Monday. So I'm not going to schedule this one ahead of time. It's going to be a bit of a surprise. I'll see if I can make up my mind before then and schedule a definite time. And then that way you can plan. Okay, yeah. So anyways, thanks so much for watching, and I'll see you next time.